Today we're going to continue our work in section 10.5 by extending into the world of combinations. So you've done permutations. Now we're going to go to combinations. Now I will give you a heads up, you are going to need your Donati's PDF menu for this, so you might want to go ahead and get that handy and then restart your video. So imagine there are 12 students in your class, and you're going to be put into groups of 3 for a project. So how many different possible groups of 3 would there be? Well, first of all, it isn't 4. I mean, there will be 4 groups, but I'm asking you how many different possible looking groups of 3. So let's ponder this one. Should we do 12p3, 12 students, permutation of 3? Well, the question to ask is, does the order in which the students get into the groups matter? Or is it just who is in the group? So if you are in this class, do you care in what order you were chosen in that group, or do you care about who's in your group? Well, putting objects into groups where the order in which they get there doesn't matter, just the final mix, that's a combination. So yes, making groups for a class project, a lot of times you guys don't even know who got put into the group first, and no one's ever asked. See, that's because what's important is just what's the final mix. What all is there, not how it got there. Now, I don't want to go deal with the group problem at the moment because that's a little bit bigger. Let's go smaller so that we can analyze. And let's go to sugar. Let's say you have 5 sundae toppings. Chocolate syrup, rainbow sprinkles, of course, nuts for those who like those, fresh whipped cream, and Oreos. How many different 2-topping sundaes are there? So say you get to pick any 2 of these toppings. How many different ways could you pick 2? Because this is such a small problem, we can actually list them out. I'm going to use abbreviated first letters for this. So I could have my first column, I'm going to be very systematic. Chocolate with sprinkles, chocolate with nuts, chocolate with whipped cream, chocolate with Oreos. Then I go to the second thing, sprinkles, and I match it with each of the other, and then nuts with everybody, and then whipped cream with everybody, and then Oreos with everybody. Are all 20 of these options unique sundaes? Or do we have any duplicates where it's the same sundae? So think about that. Any duplicates? I saw a bunch. Chocolate with sprinkles and sprinkles with chocolate are the same sundae. I know some would say, yes, but it makes a big difference where the sprinkles land. Sure, for appearance sake, it's prettier if the sprinkles come after the chocolate. But when you go to eat that sundae, it's not going to taste different if the sprinkles get under the chocolate. And like most small children, they just sort of mix everything into one big mess anyway. So we have 10 repeated sundaes here. There are really only the 10 that aren't highlighted. That's it. There are only 10 different ways of doing this. If we had done 5p2, we would have had 20. Oops, misspelling there. So what went wrong? Well, that's the big problem here is sundaes are combinations. The order in which the toppings land don't change the flavor, they just change the appearance, and so we end up counting things too many times. So we can't use the straight out p permutation calculation. We have to adjust for that repeat thing. Just like the multiple letters and circular seating, we have to adjust for the fact that once we don't care about order, the repetition can be a problem. Now, if you have 2 toppings, there are only 2 ways you could arrange 2 toppings and have it be the same. So like chocolate with sprinkles and then sprinkles with chocolate. 2 ways of writing the same combination. So if I use P, I end up with twice as many because every one of those could be written 2 ways. Now, let's try it again. Let's say you have 5 sundae toppings and you want 3 topping sundaes. So I went through and got all my 3 topping sundaes. There they are. I had 10. Now, if I had done a permutation, I would have said 5p3 because I have 5 toppings and I'm taking 3 of them. And that would be 5 times 4 times 3, which is 60. But that's too many. We came up with only 10. How in the world did 60 become 10? Well, let's use the chocolate sprinkles nuts combo sundae. How many ways can I rearrange the chocolate, the sprinkles, and the nuts in the listed letter order and have it really just be the same 3 toppings? Well, there are 6 ways of doing it. That means that every one of the things in my list is being counted 6 times in the permutation. So now let's get to the combination. Let's do the math. The way it works is that to do a combination, and now you see we have C for combination, it's a permutation divided by the repeats. Remember for repeated letters, how you would divide by 3 factorial if you had 3 E's in your name? Well, if we have 3 toppings being picked from, 3 factorial is going to be the repeats. Now, if I translate that into here's the permutation formula, and then there's the extra r factorial, this is a math formula. I'm going to tell you guys, this is programmed into your calculator. And do I think you're going to do this by hand? No. Do I think you're going to memorize this formula? No. Are you going to use your calculator? You betcha. But it's always good to know where it comes from, to know why it's doing what it's doing, so when you get answers, they make more sense. And that's what makes a mathematician different than just any other person. Mathematicians want to know why things work. Where do they come from? So that we can understand what makes them so cool. So now, knowing that you're just going to be pushing buttons on your calculator to do the math, let's do some math. I want to show you, just in case you don't have a calculator handy, let me show you the way I do it. This is something I learned long time ago when I was a student. Let's say I had 6 sundae toppings and I know I'm going to take 4 at a time. So the way I always learned to do it was I'd set up a fraction with 4 blanks both top and bottom. On the top, I'm going to take care of the how many toppings I have to choose from, and I'm going to make 4 choices, so that's why I have 4 parentheses. In the bottom, I'm going to put all of the number of ways 4 toppings could be repeated. So then I fill in the numbers like this. If in the top I'm going to choose from 4 toppings, I have 6 toppings I could pick first, then 5 left for my second choice, 4 for my third choice, and 3 for my fourth choice. Now since there are 4 toppings I'm picking, and I could have picked them in any order, I have to divide by 4 factorial. That's my repeat. So I write out 4, 3, 2, 1. So for me, this would be 6C4. I go 6, 4 numbers down, then I start with 4 and go down to 1. That's how I think about this. Then what I do is instead of multiplying all this out, I notice I have a 4 in the top and a 4 in the bottom, a 3 in the top and a 3 in the bottom. I have a 6 and a 2 that can divide with each other. And so I do this, and I'm left with 3 times 5. There are 15 4-topping sundaes. Could I have just typed in 6C4 in my calculator? Yes. But I wanted you guys to just see another strategy. All right, you try it. Go to your Donati's menu, and I want to know how many different 5-topping pizza combinations could we make? So just the toppings, okay, 5 toppings at a time. And go down to the pasta sauces, and how many different combinations of 2 sauces could you put if you wanted to like mix sauces? I know it might be kind of gross, but let's just go with it. Go ahead and pause and try it. Now, depending on how you counted, last time I looked at the menu, I counted 23 different toppings that Donati's offers. So there are 33,649 5-topping combinations you could make. And that's just the 5-topping combinations. That doesn't go through more. So 33,649 different pizzas that would have 5 toppings on it. With the sauces, I counted 7 different sauces. And when you take them 2 at a time, that's 21 flavor combinations. Gross. All right, let's go to some probability. At the local sandwich shop, you get a combo meal that consists of a sandwich, a choice of 2 sides, and a drink. So here's the menu. You've got 5 different kinds of sandwiches, and then 7 different kinds of sandwich toppings, and then 4 different sides. You get to pick 2 of those. And then they have 7 different drinks. Okay, how many different combinations of the 2 side dishes could you make? Did you get 6? Yeah, 4 side dishes, choosing 2. 4 in combinations of 2. So there'd be 6. Now, let's say you make the mistake of sending your younger sibling, who has no idea what kind of side dishes you like, to get your lunch, because, that's a smart thing to do. What's the probability that you'll end up with the coleslaw and the fruit salad, knowing that your sibling's going to be doing just a random guess? Well, if you guessed 1 out of 6, you're right. Coleslaw matched with fruit salad, there's only one way to do it, and there are 6 ways those things can get paired off. So that's about a 17% chance that you'd get the 2 you wanted. Okay, so 6 ways you could choose your 2 sides. Let's say you like 3 toppings on your sandwich. How many different 3 topping combinations would be possible? Feel free to pause and figure it out. Well, there were 7 toppings. Oil and vinegar is like together, it's in a bottle and they squeeze it on. So 7 toppings, you were going to pick any 3. There are 35 ways you could do that. All right, so now how many possible combo meals could you make? By picking a sandwich, picking a 3-topping combination, picking a 2-side combination, and picking a drink. Let's see. 5 sandwiches, 35 ways to mix the toppings, 6 ways to mix the sides, and 7 possibilities for drinks. This is a basic counting principle. 5 times 35 times 6 times 7. There are 7,350 different combo meals you could make. Isn't that crazy? So then what's the probability you'd end up with a turkey sandwich, coleslaw, fruit salad, and a tea? If you were to randomly order, which would be weird. Well, there's only one way to end up with a turkey sandwich. There was no specification about the topping, so there are 35 ways that could have happened. And then there's only one way to get my coleslaw fruit salad, and then one way to get tea. So there'd be 35 ways to end up with the turkey sandwich, and assuming we had the 3 toppings. And so then the probability of the turkey, the coleslaw fruit salad, and the tea is 35 out of 7,350, or about 0.4, 0.5%. Good to know, right? So when you do the math, the key here is to ask yourself, does order matter? Now, let's talk about locker combinations for just a second. Locker combinations, air quotes, are not combinations. They're permutations. Order matters in that little sequence of numbers. This is false advertising, but what can I do about it? What about making those roommate groups for the DC trip? That's just a combination. I don't recall any of you asking about, well, who got put in that room first? All you were interested in is who's in your room. Getting in line for food somewhere? That's a permutation. If you're getting in line for food at a picnic or something like that, you probably want to be first or second or third, towards the front of the line, so that somebody doesn't eat all the chocolate chip cookies and leaves you with something like the oatmeal raisin cookie, which are delicious. So it matters in where you fall in line for food. Something like getting in line to buy season tickets for the Cubs or the Sox or something like that. Yeah, the where you fall in line makes a big difference. So when you do this, you just have to ask, is it a combination or a permutation? So that you know, are you pushing the button for combination or permutation? Good luck and have some fun with this.